Good day. For those of you who do not know me, my name is Douglas Harder, and in this topic we're going to look at a different interpretation of the inner product. So in this topic we will interpret the inner product but using the adjoint. Recall that the inner product for real n-dimensional vectors is given by this sum. We are just multiplying the entries of the matrix pairwise and adding the results. If the vectors are complex valued, then to calculate the inner product, we have to take the conjugate of the entry in the first vector and multiply it by the corresponding entry in the second vector and then sum all of those up. This is, again, to remind you, to ensure that the inner product of a vector and itself is never zero unless the vector is the zero vector. Recall that when we perform a matrix vector product, we are multiplying a row of the matrix times the corresponding entries of the vector element-wise and adding the result. So, for example, to get the second entry of the result, we would calculate 2 times 1 plus 4 times negative 1 plus 2 squared plus 1 times 3. Now, if we interpret the transpose of a vector to be a row vector, sort of like a row within a matrix, then it follows that the inner product of u and v is equal to the multiplication of u transpose times v, which may be, for example, this row vector here. So u itself is a column vector 2, 4, 2, 1. We haven't really used the term column vector in this course anyway. Vectors are vectors. However, notice how the multiplication is the same as we did above with matrix vector multiplication. So again, 2 times 1 minus 4 times 1 plus 2 times 2 plus 1 times 3. Now, if a matrix is complex, there's no change to how matrix vector multiplication is performed. Once again, we just multiply the corresponding entries in a row of the matrix with the entries of the vector and add them together. We are not taking a conjugate anywhere. All we do is multiply, for example, 2 minus 4j times 1 plus 4j. If, however, we transpose the vector and conjugate the entries, we actually get the complex inner product. So if our vector was u is 2 plus 4j, 4 minus 5j, 2 minus plus 6j, and 1 minus 3j, the conjugate transpose of that vector would be this vector here with each of the entries conjugated, and it is now a row vector. And so to calculate the inner product, once again, we just multiply the corresponding entries now that we've already taken the conjugate. Following this topic, you now understand that an alternative interpretation of the inner product is to define the so-called adjoint of a vector, which converts the vector into a row vector, or a row within a matrix. And in the case of a complex vector, simultaneously taking the conjugate of each of the entries. Consequently, this results in the same value as taking the inner product. And sometimes you will see this used, especially in, for example, the programming language MATLAB. Here are the references, acknowledgments, the colophon, and a disclaimer. Cheers!